Let me start with a very simple question. What do black holes have to do with superconductors? And a first possible answer to that question is totally obvious. Nothing at all. And that would indeed be a very sensible answer because indeed black holes and superconductors seem to be totally unrelated. Black holes are objects up in the sky so massive that the gravitational pull is so intense that not even light can escape the gravitational field. Superconductors, on the other hand, are materials with amazing electrical properties that we can engineer down here comfortably in our labs down on Earth, but whose physical properties are certainly not governed at a fundamental level by gravitational physics as black holes are. But a second possible answer is maybe there is more than meets the eye. Perhaps physical principles can be distilled that secretly applies to both in such a way that both systems, different as they seem, may in fact be different manifestations of the same physical phenomenon. And answer number 2 is a very exciting possibility. My work as a Marie Curie Fellow at Harvard is precisely devoted to try and answer these kind of questions. Theoretical physicists like me are excited about these possibilities because not only the objects under study are very interesting in their own right, like black holes and superconductors individually are, but also because these secret relations between the physics that governs both of them may be telling us something very, very deep about how the physics laws govern the world at a fundamental level. Maybe these secret interrelations correspondences may be hinting towards a set of simple rules, of simple physical laws that describe all of physics or a significant part of it in a unified way. And many of us think that string theory is that unified framework. Now, string theory is all about unification. And unification ideas, the attempt to provide a unified account of many apparently different phenomena within the same descriptive scheme, has been a major guiding principle in the quest towards finding the physical laws that rule our world at deeper and deeper levels. Sir Isaac Newton, back in the 1600s, realized that the motion of planets up in the sky and the motion of falling apples down here on Earth is actually governed by the same physical effect, gravity. That is totally obvious for us 21st century people, but it wasn't so back in Newton's time. 200 years after Newton, Maxwell realized that, again, two apparently different phenomena, electricity and magnetism, are actually two different manifestations of the same physical laws that we now call electromagnetism. But we now know that Newton's theory can't be the end of the story as far as the theory of gravity is concerned, because it leaves out a very important issue. How is it that gravity actually works? And how is it that the sun can influence the motion of planets, of objects that are millions of miles away? Well, that question was only answered by Einstein in 1916 when he proposed his theory of general relativity. And general relativity is the fantastic idea that gravity is a deformation in the very fabric of space-time itself. According to Einstein, a massive object curves and warps the surrounding space around it, and like the sun, for example, and the planets move in basins in that curved space that we perceive as orbits. Likewise, apples fall from apple trees because the Earth curves the surrounding space and tries to warp and bend everything towards it. So Newton's theory of gravity and then Einstein's improved theory of gravity and Maxwell's electromagnetism unify different phenomena. But can we do better? Can we find a unified prescription that accounts for both gravity and electromagnetism within the same descriptive scheme? Well, shortly after Einstein proposed his theory of general relativity, Theodor Kaluza came up with a very extravagant idea, very bizarre idea. Kaluza assumed that space-time is not four-dimensional, but actually five-dimensional. That is, on top of the usual time and three spatial dimensions, Kaluza assumed that there is a fourth spatial dimension, so that space-time is five-dimensional, and this fourth dimension, for some reason, we just don't see. But what Kaluza showed was that the laws of five-dimensional physics account and reproduce four-dimensional general relativity, that is our conventional theory of gravity, combined with our conventional theory of Maxwell's electromagnetism. Amazing. Essentially, the reason why Kaluza's trick works is that in five dimensions, there is more room to accommodate what, from a four-dimensional perspective, appear to us as different phenomena. And they are accommodated in five dimensions in an orderly and simple way. But obviously, Kaluza's proposal raises an obvious question. If there is a fourth dimension of space, why haven't we seen it? And this bothered people so much that, for example, Einstein is said to have delayed the publication of Kaluza's paper for 2 years. And that would totally kill a postdoc nowadays. Well, that puzzle was solved by my namesake, Oscar Klein. Klein said that we don't see the extra dimension, that fourth dimension, because it's curled up into a tiny little circle. In the same way that distant objects appear to us as point-like, and only we get closer, we get to see their actual dimensions. Klein proposed that at every point in four-dimensional space-time, there is a little circle that, if we were able to zoom in, we would see it arising. Now, beautiful as the idea of Kaluza-Klein is, we now know that it can't be totally correct. For two reasons, essentially. Reason number one is that even though it unifies gravity and electromagnetism, it leaves out other equally fundamental interactions. And these are the interactions that govern the subatomic world, the physics of the very small, from atoms to nuclei and particle physics processes. But most importantly, while these interactions are known to comply and obey the laws of quantum physics, here's the actual drama. General relativity, Einstein's theory of gravity, which is one of the cornerstones of the unified Kaluza-Klein theory, is incompatible with quantum mechanics. And that is bad news for Einstein, because what that means is that just like Newton's theory wasn't the end of the story as far as the theory of gravity is concerned, Einstein's theory isn't either. We do need a theory of quantum gravity. Now, it's easy to see with an example what goes wrong when one tries to combine general relativity with quantum mechanics. Recall that Einstein said that gravity is curvature of space-time. The more massive an object is, like a star, the more it curves the surrounding space. Now, imagine a star so massive that not even light could escape its gravitational pull. The star would become a black hole. And in such an extreme circumstance, if we were led to believe Einstein to the last consequence, we would think that space-time gets so warped and so curved that eventually breaks down and tears apart. But that can't be the right answer, because what we think is that quantum effects in that situation, in such an extreme situation, take over and change the picture dramatically. We don't know what the picture is, because we don't know how to combine general relativity and quantum mechanics, but that is a very interesting line of investigation and something that string theory tries to address as well. Now, the state of the art in particle physics is the discovery of the Higgs boson back in CERN, Geneva, Switzerland, that led to the award of the Nobel Physics Prize last year. The state of the art in cosmology is the recent discovery by a Harvard-led team of remnants of inflation, the bang of the Big Bang. And that will lead to future Nobel Physics Prizes for sure. But can we take over those unification ideas and describe within a single framework all of physics, particle physics, cosmology, the physics of the very small to the physics of the very large? And can that unified framework provide a description of quantum gravity so that we can describe black holes? And can we uncover unexpected relations between different objects, like, for example, black holes and superconductors? Well, we believe that string theory may well be that unified framework. And the basic underlying assumption under string theory is that the particles that we used to think that were the basic constituents of nature, well, forget about that idea. Forget that electrons, quarks, and so on are the basic constituents of nature, and assume that, in fact, the basic elements of nature are tiny little vibrating strings, so that the particles that we can observe in laboratories are actually different vibrational patterns of those strings. Now, the interesting effect is that the mathematical laws that describe string theory can't be formulated in a four-dimensional space-time. String theory can't be formulated in 5 dimensions either, nor 6, nor 7. It has to be formulated in 10 dimensions. So you see the old Kaluza-Klein idea taking over in 21st century physics with two differences. Kaluza assumed a 5th dimension, whereas now we are predicting that we live in a 10-dimensional space-time. And also, just like Kaluza found electricity and magnetism to be unified within his theory, in 10 dimensions, we now have more room to accommodate all of 4-dimensional physics in a simple way. All of the elements that we want to unify are there in string theory. The challenge is how to actually extract those from the theory. And there are two ways, essentially, to do that. And with these, I'll conclude. One route is to generalize and update the old Kaluza-Klein idea into this context and assume that the extra 6 dimensions are, in fact, curled up into a little tiny manifold at each point in 4-dimensional space-time. That would take this form. This form is the form of the extra dimensions is very crucial in this setting because it would determine how physics behaves from a 4-dimensional perspective. All of the masses, all of the charges, all of the physical quantities in the 4-dimensional world would be down to the shape of these extra dimensions that we don't know what it is, but we're trying to figure that out. A second route to make contact with 4-dimensional physics is to try and exploit mathematical redundancies in the formulation of the theory that turn out to relate objects as different as black holes and superconductors. Objects that are the subject of study of pure basic research like quantum gravity to actual materials that one can engineer in our labs. Objects that are the subject of research of astrophysics with something that can be engineered in cutting-edge technologies. That would be an amazing possibility. And with that, I'll conclude. Thank you.